Let's go through Activity 7. So in this activity, we're going to be working with the launch data set, which is part of a Kaggle competition where we try to predict the total profit over the first few months after a product's release. So it's real data, it's been anonymized, so the predictors are just referred to as X1, X2, etc., not to give away any sort of trade secrets. But this is a very large data set. The predictor variables number in about over 400 or so. So there's a lot of potential information that might be floating around that could potentially help us predict profit. So let's go ahead and actually restrict ourselves to a smaller subset of predictors to make the problem a little bit easier. So we're going to run the following code that is going to load in the launch data frame, and then take a subset of just the very first 6 columns here. So you can remember that if you want to refer to particular columns, you put square brackets after the name of the data frame, and then you put a comma in the middle of those square brackets. On the left of the comma refers to the rows, blank in this case because we want all the rows, and to the right refers to the columns that we want. And the shortcut 1:6 actually is just represented as 1, 2, 3, 4, 5, 6 internally here. So doing PL left arrow launch bracket comma 1:6 gives us the first 6 columns of the launch data frame, and that's what we're going to work with. All right, so question 1 asks us to start out just by fitting a multiple regression model predicting profit from our 5 predictors. So let's go ahead and fit that model. Let's call it M. And we can use the twiddle dot shortcut here because we're going to use all variables in the data frame. Profit twiddle dot, working with the PL data frame. And we want to record the values of R squared adjusted, and the root mean squared error. So we'll click run, and we find that the value of R squared, R refers to that as the multiple R squared, is 0.689. The R squared adjusted, a fairer measure of how well the model is fitting the data, is still right at about 0.69 here. And the root mean squared error, the typical error that the regression makes, looks to be about 0.2878. So the actual values of profit, and it looks like they range from maybe 3 to 5 or so, are off by what the model predicts by about 0.29 or so. All right, so the multiple regression model as fitted is very often overly simplistic because interactions play a very key role in many relationships. Very often the strength of the relationship between y and say x1 isn't necessarily a constant. It might be stronger among individuals with larger values of x2 than smaller values of x2. Or maybe it might be weaker for individuals with larger values of x4, but stronger for individuals with smaller values of x4. We want to allow for that possibility by probing a model with interactions between the variables. So what we can do is we can fit a fairly complex model considering all two-way interactions between the 5 predictor variables. So we can use this, you can do this by doing the twiddle dot squared shortcut. It works similar to the twiddle dot shortcut, except we put a caret 2 to denote the fact that we want to use all predictor variables and all two-way interactions. Notice just because it's twiddle dot squared doesn't mean we'll have the squared values of the predictors as predictors in the model, just the two-way interactions. So let's fit the model m.int and then look at a summary of it. There's going to be a lot of predictor variables. There's a total of 10 interactions. And so we see we have the predictor variables 1 through 5 themselves, the interaction between x1, x2, the interaction between x3, x4, etc. So let's see how much the model is improved, if at all, by including the interactions. Let's copy and paste the value of r squared, which we're promptly going to ignore because we know r squared always gets bigger when we add predictors into the model, even if they're unrelated to y. And instead, we're going to focus on the root mean squared error and the value of the r squared adjusted. So the root mean squared error tells us the typical size of the error that the regression is making, and we see that it has decreased just a little bit from 0.29 essentially to 0.27. So the RMSE has gone down from about 0.9 to 0.27, a slight improvement. So the values of profit are varying between about 3 and 5 or so, making the error go down from about 0.29 to 0.27. It's nice, but not a huge, amazing improvement or anything. The value of r squared adjusted has gone up from about 0.69 to about 0.72 here. So r squared adjusted has gone from 0.69 to 0.72, which is a small but nice improvement. So including these interactions hasn't made a world of difference, but it definitely has improved the model somewhat. So kind of a nice thing to consider. Now, how many of these interactions are statistically significant? Well, we can go back and look at the p-values, and anything that's less than 0.05 is statistically significant. When we add that particular interaction to the model that already contains all the other predictors, then that improves the model's predictive power here. We basically improve our predictive power more than adding just some random unrelated predictor. So which interactions are statistically significant? Well, it looks like the interaction between x1 and x2 is, the interaction between x1 and x3, the interaction between x1 and x5, x2 and x3, x2 and x5, and finally x3 and x5, for a total of 6 of the interactions. So 6 interactions are statistically significant, and so from a statistical point of view, it seems to be worth it to incorporate interactions into the model. So when we put in interactions into the regression model, we're allowing for the possibility that the strength of the relationship, say between y and x1, might depend on the characteristics of the individuals. Sometimes it might be stronger or weaker depending on, say, what the x2 value of the individuals are. So one way to look at how the interactions affect the model is to write out the implicit regression equations, but that's really hard to do because there's a lot of stuff in here. Oftentimes, a picture is worth 1,000 words, so let's go ahead and actually just peruse the interactions by running C interactions on our model with the interactions. Notice I've named it m.int just so that it has a different name than the original model. Now, because there are so many interactions, I'm going to add in the argument many equals true, so it shows us a set of interactions at a time here. So we're going to peruse all 10 fitted interactions, and we're going to report one pair, and there's probably going to be more than one pair, of variables that have a strong interaction or a weak/non-existent interaction. So let's actually just make a comment over all of them. So we'll start out by not typoing that. Here's the interaction plot between the variables x1 and x2. I'm actually going to escape out of here. Or finish these and then redo it so that I have a little bit more room to look at these interactions. So here's the interaction between x1 and x2. The plot on the left is breaking down the relationship between profit and x1. The plot on the right is breaking down the relationship between profit and x2. So for various values of the other variable. So in this case, this dotted line shows us what the relationship between profit and x1 looks like for individuals with large values of x2. The solid line is the equivalent relationship, but among individuals with smaller values of x2. So when an interaction exists between two variables, the nature of the regression, or what the regression looks like, changes quite substantially depending on the values of that third variable. And so here, we're seeing that the relationship between profit and x1 changes quite noticeably between the three possible values of x2. So this has a very strong slope, very positive slope. This one has a much weaker slope. So I would say that x1 and x2 have a pretty strong interaction going on. Same sort of story here. The nature of the relationship between profit and x2 looks to change depending on the x1 values of the individuals we're comparing. We see that for small values of x1, it's relatively weak. The slope isn't all that steep. But for large values of x1, the relationship between profit and x2 is actually pretty strong here. All right, pressing enter to go on to the next set, we see that these implicit regression lines here really don't change all that much when we break down the relationship based on the value of x3. So this is showing the relationship between profit and x1 for individuals with large values of x3, medium values of x3, and then small values of x3. And so we see the slopes, while they're, a little bit different here, they're not all that much different. The slope doesn't change by that large of an amount. So I'm going to say that this interaction is fairly weak. Whenever we see intersecting lines, that indicates, hey, we have a strong interaction. Whenever the lines are mostly parallel, we say the interaction is weak, if it exists at all. All right, well, what about x1 and x4? Well, these lines are almost parallel here. The strength of the relationship between profit and x1 is about the same regardless of the x4 values of the individuals we're comparing. Same with reversing the way we interpret that. So x1 and x4, very weak. And this looks to be fairly weak as well. The nature of the relationship between, say, profit and x5 looks to have about the same strength regardless of the x1 and values of the individuals we're looking at. X2 and X3, well, this one kind of straddles the fence. We do see a little bit of a difference in slopes here, definitely stronger for individuals with larger values of X3 versus smaller values of X3, but it's not a huge difference. So I'm going to go ahead and just say, all right, let's have this one be a strong one. It's not that strong, but it's not that weak. It's kind of in the middle. X2 and X4, well, this one looks to be relatively strong. Notice that the relationship is negative for individuals with large values of x4. The relationship between profit and x2 actually has a negative slope there, but a positive slope for individuals with smaller values of x4. So I'm going to say x2 and x4 are fairly strong. Here's a very strong interaction where when we look at the relationship between profit and x2, the relationship is very strong and negative when the individuals have large values of x5, but it's actually somewhat positive when we look at individuals with small values of x5. So this is a very strong one. I'm going to put that with asterisks just to remind myself how strong that was. Going on to the next one, x3 and x4. Well, these lines are almost parallel, so this is pretty weak. x5 and x3, well, we see some difference in slope. It's positive when x5 is large, but negative when x5 is small. So another fairly strong interaction going on. And then finally, one more. All right, these lines are roughly parallel. We would say that the interaction is weak if it exists at all. The nature of the relationship, the strength of the relationship between profit and x4 is about the same regardless of the value of x5 we're focusing in on. And same thing for the relationship between profit and x5, about the same regardless of the value of x4 that we're focusing in on. Okay, so not too surprisingly, this seemed to be the strongest interaction going on. In part D, I ask you to fit a model predicting profit from just x2, x5, and their interaction. So we're going to say, I'm going to call it m.25, just to name it something different. And the way that we'll do this is with a shortcut. We'll say profit, our y variable, twiddle. And then to do the model with x2 and x5, along with the interaction in the model, I'm going to do x2 times x5. That lives in the PL data frame. And what we're going to do is we're going to visualize this model by using the command visualize model. So we'll fit it, boop, and we'll visualize it. And one thing that we see is that the interaction term, not too surprisingly, is statistically significant. The model significantly improves when adding the interaction term to the model that just has x2 and x5 separately as predictors. And what we see is that, sure, the nature of the relationship between profit and x2 looks to be noticeably different depending on the x5 values of the individuals that we're comparing. We see that the red line is giving us the relationship between profit and x2 when the x5 values of the individuals are large. And the blue line here gives us the relationship between profit and x2 among individuals whose x5 values are small. So one thing we notice is that the relationship is fairly weak when x5 is large, but relatively strong when x5 is small. Kind of flipping the coin here, we see that the nature of the relationship between profit and x5 actually changes quite a bit depending on what value of x2 we're focusing in on. If we focus in on individuals with small values of x2, the blue line, we see the relationship is somewhat positive, and the story completely changes if instead we focus in on individuals with large values of x2. Among individuals with large values of x2, the relationship between profit and x5 is actually negative. All right, so the implication of a statistically significant interaction means really quite a few things. It means that the strength of the relationship between profit and x2 depends on what value of x5 I'm looking at, and vice versa. And it also means that the expected difference in profit between two products that differ in x2 by 1 unit depends on exactly what the common identical values of x5 that I'm actually focusing in on. So let's refer to the plot on the right. We'll notice that when x5 is very close to 0, we see that the difference in the profits, depending on the value of x2, is really quite large. We see that there's a very large spread between the blue and the red line here, indicating that the difference in profits when we compare otherwise identical individuals, say with values of x5 equal to 0, it's really quite large here. So the expected differences in profit between products that differ in x2 are really quite big. So the difference in expected profits when x5 is close to 0 is quite large, depending on the value of x2. Now, when x5 is instead near 1500, we see there's actually a relatively small difference in profits. The value of x2 doesn't really matter as much. There's a smaller spread here. The value of x2 matters a lot when the value of x5 is close to 0. So when x5 is near 1500, the expected differences in profit between products that differ in x2 is relatively small. So it looks like x2 matters a lot when x5 is small, but x2 doesn't matter that much when x5 is large. All right, so what have we been talking about already is that the other implication of a statistically significant interaction is that the strength of the relationship changes. So the strength of the relationship between profit and x5 depends on what the x2 value of the individuals that we're focusing in on. So once again, we're going to look at the plot on the right, and we want to describe how the strength of the relationship changes between profit and x5 as we consider x2 values of products that are larger and larger. So if we start out with products with x2 values that are small, the blue line, we see that the relationship is somewhat positive. And as we increase the x2 values of the products that we're comparing, we go from the blue line to the black line, then finally to the red line for large values of x2. So what we see is that the relationship actually flips sign. So for small values of x2, the relationship between profits and x5 is somewhat positive. As we go to products with progressively larger values of x2, however, the relationship begins to weaken. The slope gets closer to 0. Notice as we go from the blue line to the black line, at some point that line must be just parallel with the 0 slope. Then the relationship becomes negative and stronger as we get to larger values of x2. So as we go from blue to black to red, the relationship initially weakens, eventually becoming 0, and then the relationship becomes stronger and more negative here. So a pretty complex relationship going on. That's pretty interesting. All right, now let's look at the plot on the left, and this is showing the relationship between the profit and x2 value of the profit of the products. And let's do the same sort of thing. Let's describe how the nature of the relationship changes as we compare products with progressively larger values of x5. So when x5 is small, we're looking at the blue line here, and we see that the relationship between profit and x2 is strong and positive. As we go to products with progressively larger values of x5, we go from the blue line to the black line to the red line. And so we see that these lines have slopes that are closer and closer to 0. So the relationship between profit and x2 starts out fairly strong and positive. And as we compare products with increasingly large values of x5, the relationship between profit and x2 weakens. Never becomes negative because even at some of the largest values of x5, it's still somewhat positive, but the slope is closer to 0, so it's a weaker relationship. Whew, so that's a mouthful, and that's really why you get paid the big bucks if you're doing business analytics. Interpreting these interaction plots really takes quite a lot of work and quite a lot of words, but being able to interpret these, one of the key skills that I want you to be picking up in this class, because very often just predicting y from the individual predictors isn't enough. The relationship is more complex, and the strength of the relationship changes between y and x depending on values of third variables. These interactions play an important role. All right, question 4 changes gears a bit and asks us to do an analysis on potential outliers or influential points. So finding outliers is difficult in this situation because, as we've seen in class, an influential point may actually end up having pretty typical values for each of the predictors individually, and they may actually have fairly typical combinations of pairs of variables, but they still may be unusual in some higher order combination of them. So these influential points can hide in histograms, box plots, and even scatter plots. So we look at the influence plot instead to gauge the presence of interactions, the influence plot to gauge the presence of influential points, points that had more than their fair share of influence over the coefficients of the regression model. So we run influence plot, and we know that in order to be influential, to have a lot of control over what the values of the coefficients are, a point needs to have a large leverage, and it has to have a large deleted studentized residual, either more positive than 2 or more negative than negative 2 here. So the influential points live in the upper right-hand rectangle and the lower right-hand rectangle. Leverage is a measure of how unusual that point is with respect to the combination of x values that it possesses. Deleted studentized residual is how far away that point is from where the regression would have been going without it. So any of the points marked by x's in the upper and lower right-hand rectangles are influential points, and in some sense they have a lot more control over the values of the coefficients of the model than the other points in the data set. So how many points are influential according to our criteria here? Well, we could count that up, or we could just look to see how many points are here. 1, 2, 3, 4, 5, 6, 7, 8, 9. Well, there's 9 points. All right, the point on the very far right, this guy right here, the one with the highest leverage, turns out to belong to row 463. And one interesting thing to do is to make sure that that influential point is a legitimate observation, that we haven't added a 0 to one of the variables, we haven't deleted a 0. So let's go ahead and actually print out that row of the data frame here. So we can do that by adding square brackets after the name of the data frame. And before the comma, we put the row number that we're interested in. So 463, we leave the column number blank because we want all columns. So that's the values of the individual for x1 through x5 in profit. And let's run a summary on the data frame to see just what the distribution of values are for each of those predictors, just to see if we can spot something that makes this point unusual. Now, we know that influential points can hide in terms of just individual values for the predictors. They could have standard values for those predictors, but just be weird in some combination. So scanning through the list, we see that its profit is on the high side, but it's not the highest. Its x1 value is pretty typical here. Its x2 value is more on the high side, but not the highest, not all that unusual. Its x3 value is on, kind of in the middle here. It's not too big, too small. Its x4 value looks to be on the high side once again, but not the highest there. And its x5 value of 11, a little bit on the low side, but not the lowest either. So what we're finding is that this product here isn't that unusual in terms of its profit or any of its predictor variables. What's making it influential is kind of some higher order combination of variables here, something that we can't immediately identify from looking at the actual values themselves. So this product here has reasonably typical values for profit and the 5 predictor variables. The reason it is influential must be due to the fact that it has a highly unusual combination of values here. So we couldn't detect it just from looking at the individual variables themselves. Must be unusual in some higher order combination. Okay, so moving on to question 5. If we look at the relationship between profit and x2 just by itself, it looks like it may be nonlinear. So if I plot profit twiddle x2 in the PL data frame, my eyes pick up that this relationship may have a little bit of a curvature to it. So let's do some investigation. Let's see if we could come up with a better model by instead predicting profit from just x2 by predicting it from a polynomial model in x2. So let's fit the simple linear regression. And I'm going to call this m.2 here, just to denote that we're doing this from x2. Predicting profit from x2 in the PL data frame. So let's fit it, and then run choose order to see if a polynomial model might fit better. So we click this. And what we see is that as we go from the simple linear regression, basically the order 1 polynomial, the r-squared adjusted actually leaps up by quite a bit. So going to order 2 makes the r-squared adjusted go up to 0.504. Order 3 makes it go up a little bit higher. And then actually adding higher order powers doesn't really help it out. It causes the r-squared to actually get a little bit worse. So, all right, what order do we pick? Well, we have this 0.005 guideline. Now, what this guideline means is basically don't necessarily go for the model with the highest r-squared adjusted. Go for a simpler model if possible. Basically, take that highest value of the r-squared adjusted and subtract off 0.005 from it. And what we want to do is choose the simplest model that we can, the model with the lowest order, whose r-squared adjusted is at least as big as this quantity here, no more than 0.005 below the highest r-squared adjusted. So we see actually that we could get away with a second order polynomial, basically predicting profit from x2 and x2 squared, because its r-squared adjusted is high enough and simpler than the one with the overall highest r-squared adjusted. So our comment is that we would choose a second order polynomial predicting profit from x2 and x2 squared. It looks like that's good enough. And in fact, looking at the plot, we see that there's very little difference between the order 3 and order 2 polynomial, the red curve and the blue curve. For all intents and purposes, they're the same almost everywhere except for the values at the very, very left end of x2. And there are hardly any points there. There's really very little difference. There's a little compelling reason to add in that third power of x2 into the model, where it looks like this would just be sufficient. All right, so let's go ahead and fit the model predicting profit with all the interactions and include the relevant polynomial term. All right, so this is actually a kind of an exercise in model specification. We know that we can predict profit from all predictors and the two-way interactions with the twiddle.squared shortcut. And if we want to throw in a polynomial term, what we actually need to do is take out the original predictor, x2 in this case, and then add in our polynomial model. So poly x2, comma 2, take x2 and actually predict it from x2 and x2 squared. So we'll use the PL data frame here. We'll run it and then look at a summary of that model. Okay, so some follow-up questions. Is the highest order of the polynomial statistically significant? Highest order means the highest power of that predictor that appears. And so we look at the poly x2 squared term, and we see that, yep, sure is. Yes, the p-value is much less than 5%. In fact, it's 4.19 times 10 to the minus 8 power, way below 0.05. Has the model improved in terms of r-squared adjusted and root mean squared error? Well, let's copy and paste this r-squared adjusted, and let's copy and paste this root mean squared error. And let's compare that to the model that we had without that polynomial term. So with all two-way interactions, that was a long time ago, we have an r-squared adjusted and root mean squared error of those two numbers. Let's go ahead and just copy and paste that down here just so that we can compare. So we see that the r-squared adjusted has increased from about 0.72 to 0.73, and the root mean squared error has decreased from about 0.274 to maybe 0.269. So the model has improved, but just by a little bit. So the adjusted r-squared has gone from about 0.72 to 0.73, and the RMSE has decreased from 0.274 to 0.268. So sure, it's an improvement, but it definitely is not a big improvement. But hey, any little bit can potentially matter in business analytics. All right, question 6. Imagine x3 and x5 represent two specific things: the number of advertisements of the product on CNN.com and on FoxNews.com. Let's also imagine that x1 corresponds to the estimated total number of people who saw an internet ad for the product. So if that's the case, then the quantity x1 over x3 plus x5 represents the total number of people per ad who saw the product, and that could be a worthwhile predictor. So we're free to invent any sort of new predictors that we want, and maybe sometimes our model improves quite a bit if we stumble upon the right variable. All right, so how do we actually, go about creating a new variable? Well, in this case, I'm going to call the new variable PPA. So just like I define anything, I'll do PPA, then the left arrow. And then what do I want to do? Well, I want it to be x1 over x3 plus x5. But all those variables live in the PL data frame, so I need to refer to that specifically with the PL $sign. So PL x1 divided by PL $x3 plus PL $x5. We'll run that. And what we'll see is that the value PPA is now in the environment. And now we're going to go ahead and add that to the PL data frame. So we can do that just by saying the name of the data frame and the $sign, and then the name that we want to give the column. Why not just call it PPA here? So we'll set the PPA column of the PL data frame just to be equal to this vector we just created. So we'll do that. And now what we're going to do is we're going to fit a simple linear regression predicting profit from it. So I'll call that M PPA, LM profit twiddle PPA data equals PL. And let's look at a summary of it. All right. So, is the regression statistically significant? Yep, sure thing. It looks like the p-value of the regression model is less than 5%. So this simple linear regression is statistically significant. The p-value is less than 5% here. And gosh, was that everything that I asked? Create a variable, add it. Is it statistically significant? Yep, it sure is, but you'll notice that this one variable, this new variable alone, really doesn't provide a very useful model here. Notice its r squared adjusted is 0.02, which is phenomenally less than the r squared adjusted we were getting from those 5 predictors and all 2A interactions and the polynomial term. So I definitely wouldn't want to just use this one predictor as my model here. It may help to actually add this to the model with all 2-way predictors in that polynomial term, but we'll kind of skip that investigation for now. All right, last question, question 7 here, deals with extrapolation. So with multiple regression, we need to check to see if the combination of x values at which we're making our predictions are combinations that the model has seen before. Maybe not exact values, but similar combinations here. So it's difficult to tell because very often we can come up with a combination of x values where each individual value of x is pretty typical, but the combination is really weird and something we haven't seen before. So let's imagine that we're going to make predictions for 2 products here. So one product has an x1 value of 8,000, an x2 value of 3,000, an x3 value of 100, etc., etc. And what I've defined these numbers to be are such that individually at least, both these products have fairly typical values of x1, typical values of x2, etc., etc. So I just want to make sure, hey, are these unusual combinations of predictors to be making predictions at? So let's run extrapolation check from that model with all 2-way interactions, not with the polynomial term. I could do that here, but I won't. Let's run the extrapolation check, and let's see what the results are. All right, so what we focus in on are the numbers under percentile. This tells us the fraction of the data points used to build the model that are closer to the center of the predictor data cloud than the points at which I'm trying to make predictions at. Large values can get scary. Basically, observation number 1 is farther away from the center of the predictor data cloud than 99.4% of the points used to build the model. So most likely, this is actually going to require extrapolation. It's in a very unusual position. It has a very unusual combination of x values, and I'd be worried at making a prediction there. It may be the case that the nature of the relationship changes by the time we predict that far out into the outskirts. I'd be fine making a prediction for observation 2 because only about 43–44% of points are farther away. It looks like I'm right in the thick of things at a pretty typical combination of x values if I make a prediction there. So the first observation probably requires extrapolation. It is farther away from the center of the predictor data cloud than 99.4% of the points used to build the model. So this is probably a very unusual and unseen combination of values to predict at. The second observation, well, we think it's fine. Should be fine. It is farther away than 56.7% of the points used to build the model. So there are probably plenty of other points whose x-value combinations are pretty similar to this combination. So we should be okay. All right, so that is the monumental Activity 7, kind of getting to the pinnacle of doing multiple regression with quantitative variables. And hey, if you can do this sort of an analysis, you would be a phenomenal asset to a company, and they would hire you just like that, because this sort of analysis, as you see, pretty subtle, pretty difficult, but very informative.